Yeah, so I'll be talking about momentum methods and acceleration and stochastic optimization, and this is joint work with Pratik Jain back in Microsoft Research in India, Shyam Kakade and Rahul Kidambi at the University of Washington, and Aaron Sidford from the Stanford University. Okay. Let me start by giving a brief overview and context of our work. As many of us might already be aware of, optimization is a really crucial component in large scale machine learning these days, and stochastic methods such as stochastic gradient descent are some of the workhorses that power these optimization routines, right. There are three key aspects with which stochastic gradient descent is used in practice in these optimization routines, and which are crucial for its good performance. So, the first one is mini batching, where we compute the stochastic gradient not over a single example, but rather over a batch of examples. The second one is what is known as model averaging, where you run independent copies of stochastic gradient descent on multiple machines and try to somehow combine the results to get a much better model than each of them alone. And finally, there is a technique from deterministic optimization called acceleration or momentum, which is also used on top of stochastic gradient methods. And all of these three things seem to be important for the good performance of stochastic gradient descent in practice. However, from a understanding point of view or a theory point of view, we still do not have a very good understanding of what are the effects of these methods on stochastic gradient descent, and do they really help, and if they help, how are they helping, and all these various aspects with which these are used, right. And our work here is a thorough investigation of all of these three aspects for the specific case of stochastic linear regression. Okay. The reason that we consider stochastic linear regression is because the very special structure of the problem lets us gain a very fine understanding of each of these three aspects, and at the same time the results and intuitions that we gain from this seem to have some relevance to the way to even more complicated problems such as training deep neural networks, and I will touch upon that topic towards the end of my talk. Okay. In this talk in particular, I will be talking only about the last aspect, which is acceleration and momentum algorithms on top of stochastic gradient descent. Okay. So, this is basically the outline or the high level subject of my talk. Okay. Let me now start by giving a brief introduction to deterministic optimization. A lot of you might already know this, but I thought if I just spend a few minutes on this, it might be helpful to follow the rest of the talk even more easily. Okay. So, bear with me if you already know a lot of this stuff. So, gradient descent is of course one of the most fundamental optimization algorithms, and given a function f, we start with a point w0, and at every iteration we move in the negative gradient direction. Okay. And as I mentioned, the problem that we will be considering in this talk is that of linear regression. Here we are given a matrix x and a vector y, and we wish to find a vector w which minimizes the L2 square of x transpose w minus y. Okay. This is the linear regression problem, and as you can imagine, this is a very basic problem and arises in several applications, and people have done a lot of work in understanding how to solve this problem well. In particular, the first question that comes to our mind is what is the performance of gradient descent when you apply it to the linear regression problem. Okay. In order to answer this question quantitatively, we need to introduce this notion of condition number, which is just the ratio of the largest to smallest eigenvalues of the matrix XX transpose. With this notation, it turns out that gradient descent finds an epsilon suboptimal point. What I mean by that is that f of w minus the optimum is at most epsilon. So, gradient descent finds an epsilon suboptimal point in about condition number log of initial suboptimality over target suboptimality number of iteration. So, this is the number of iterations that gradient descent takes to converge to find an epsilon suboptimal point. Okay. The next question that comes to mind is whether it is possible to do any better than this gradient descent rate, and there is hope, because gradient descent, even though it has seen gradients of all the past iterates, it only uses the current gradient to make the next update, right. So, the hope would be if there is a more intelligent way to utilize all the past gradients that we have seen to make a better step, then maybe we can get a better rate, and this intuition turns out to be true, and there are several famous algorithms which actually achieve this kind of improvement. Some of the famous examples include conjugate gradient and heavy ball method, as well as Nesterov's celebrated accelerated gradient method. Okay. The last two methods in particular are also known as momentum methods, and we will see why they are called momentum methods. So, as a representative example, let us look at what Nesterov's accelerated gradient descent looks like. While gradient descent had just one iterate, Nesterov's accelerated gradient can be thought of as having two different iterates. We denoted them with Wt and Vt, and there are two kinds of steps, gradient steps and momentum steps. So, from Vt we take a gradient step to get Wt plus 1, and from Wt plus 1 we take a momentum step to get Vt plus 1, okay? And then we again take a gradient step. So, it alternates between these gradient and momentum steps, and this is the Nesterov gradient algorithm with appropriate parameters, of course, okay? And this is how it looks in the equation form. The exact form is not important, but one thing that I want to point out here is that the amount of time taken for a single iteration of Nesterov's accelerated gradient is pretty much the same as that taken by one iteration of gradient descent. So, in terms of time per iteration, it is exactly the same up to constants, okay? However, the convergence rate of Nesterov's accelerated gradient turns out to be square root of condition number log of initial over target for optimality, okay? So, if we compare it to the rate of gradient descent, we see that we get an improvement of square root of condition number, and condition number is defined as a max over min. So, it is always greater than or equal to 1. So, this is always an improvement over gradient descent, okay? And this is actually not just a theoretical improvement. In fact, even on moderately ill conditioned problems, here we are looking at a linear regression problem where the condition number is about 100. We see that Nesterov's gradient, which is in the red, is an order of magnitude faster than gradient descent, which is in the blue. So, this actually really has practical advantages in getting this better convergence rate, okay? So, this is all I wanted to say about deterministic optimization. If we come to the kind of optimization problems that we encounter in machine learning, we usually have a bunch of training data x1 y1 up to xn yn. Let us say we get all of this data from some underlying distribution on RD cross R. So, D is the underlying dimension and we get this training data. We can use whatever we saw so far to solve the training loss, which is just 1 over n summation xi transpose w minus yi whole square. So, the f hat of w that we have here is the training loss, and we could use either gradient descent or Nesterov's accelerated gradient to solve the training loss, right. But in machine learning, we are not really interested in optimizing the training loss per se. What we are really interested in is optimizing the test loss or test error, which means that if we are given a new data point from the underlying distribution, we want to minimize x transpose w minus y whole square, where x and y is sampled uniformly at random from the same underlying distribution, okay. In order to optimize this function, however, we cannot directly use the gradient or accelerated gradient method from before, because the gradients here can be written as expectations, and we do not really have access to exact expectations. All we have access to is the samples that we have seen from the distribution. And this setting has also been well studied and goes by the name of stochastic approximation. And in a seminal paper, Robbins and Monro introduced what is known as stochastic gradient algorithm to solve these kind of problems. And the main idea is extremely simple, which is that in any algorithm that you take, gradient descent for instance, wherever you are using gradient for the update, you replace it with a stochastic gradient, where the stochastic gradient is calculated on just using a single point, right. And in expectation, because this stochastic gradient is equal to the gradient, we are in expectation doing gradient descent, and we would hope that this also has good convergence properties. And moreover, if you look at the per iteration cost of stochastic gradient descent, it is extremely small. So, the stochastic gradient computation just requires us to compute that thing in the red for the linear regression problem, which requires us to just take one look at the data point, and that is about it. So, making each of these stochastic gradient updates is extremely fast, and because of this efficiency, it is widely used in practice, okay. While I gave you this example on top of gradient descent and how to convert it into stochastic gradient descent, you could apply the same framework to any deterministic optimization algorithm. If you take heavy ball, you will get a stochastic heavy ball. If you take Nesterov's accelerated gradient, you will get stochastic Nesterov accelerated gradient. The recipe is just simple. You will have an update equation, just replace gradients with stochastic gradients, and you get these stochastic methods, right. Okay, so now let us again come back to stochastic gradient descent and try to understand the convergence rate of stochastic gradient descent for in this stochastic approximation setting, okay. For illustration, if we just consider the noiseless setting where y is exactly equal to x transpose w star, so there is some underlying truth w star, and our observations y are exactly equal to x transpose w star, then the convergence rate of stochastic gradient stochastic gradient descent again turns out to be very similar to that of gradient descent, which is condition number log of initial over targets of optimality, but the definition of condition number here is different compared to what we had in the gradient descent case. Okay. But with this new definition, the convergence rate looks essentially the same. If we consider the noisy case where y is equal to x transpose w star plus say 0 mean additive noise, then there will be an extra term in the convergence rate which depends on the variance of the noise term. So, sigma square, which we do not here with sigma square. Okay. So, let me try to summarize all of the discussion so far in a table. Yeah. What is theta? Yeah, so it has some additional log factors in whatever is inside the brackets. Okay. So, summarizing all our discussion so far, in the deterministic setting, we saw that gradient descent has a convergence rate of condition number log of initial over targets of optimality. So, it depends linearly on the condition number, and we saw that there are these acceleration techniques which can improve by a factor of square root condition number, right. And in the stochastic case, stochastic gradient descent has again this kind of convergence rate, which is a sum of the noiseless part and then one thing that comes from the noise. And the broad question that we ask here is whether accelerating stochastic gradient descent in the stochastic setting possible, just like what we were able to do in the deterministic setting. Okay. And I need to clarify the question a little bit more, because it is well known that the second term that we have here, which is sigma square d over epsilon, is actually statistically optimal. So, there is no way, no algorithm can improve upon the statistically optimal rate. There is information theoretic lower bounds that is the best you can do. So, when we talk about accelerating stochastic gradient descent, what we mean is, can we improve this first term, where for instance we have a linear dependence on kappa, can we perhaps improve it to a square root kappa, for instance. Okay. Yeah.
But here I can just use a direct method to jump directly to the solution. So you mean optimal in the class of gradient first order?
Yeah,
methods?
yeah, optimal in the class of first order methods.
So what about second order methods?
Second order method, I mean, even within first order methods, if you are not interested in a streaming algorithm, you could just take the entire covariance matrix and try to invert it, again using maybe a first order method. But we are looking at streaming algorithms which are kind of actually what are used in practice. Yeah.
But here you could also use conjugate gradient methods, right?
Again, I mean, you can use that on the empirical loss. Yeah. For the streaming problem, conjugate gradient methods, I don't know, they have not been studied for the streaming kind of setting. Yeah. For the empirical loss, we could do either second order methods or conjugate gradient, all of, like any of the things. Yeah. Okay. So before I try to answer this question, let me try to convince you why this question is worth studying. And the reason is that in the deterministic case, firstly, we saw that acceleration can actually give orders of magnitude improvement over unaccelerated methods, and there is reason to hope that the same thing might be true even in the stochastic case. And in fact, even though we do not really know of a accelerated method in the stochastic setting, people are in practice people do use the stochastic heavy ball and stochastic Nesterov that I just mentioned in training deep neural networks, so much so that in fact if you look at any of the standard deep learning packages like PyTorch or TensorFlow or CNTK, we will see that SGD actually means SGD with momentum. So, there is this default parameter of momentum, and SGD is usually run with this additional momentum parameter, even though we do not really understand what exactly it is doing and how it is helping, if at all it is helping, and so on. Okay. So, in the practical context, people are using these things, but at the same time we do not really have a full understanding of whether this even makes sense in the stochastic setting. And finally, in terms of related work on understanding acceleration in the stochastic setting, there are some works by Ghadimi and Lan in particular, which try to understand whether acceleration is possible in the stochastic setting, but they consider a different model compared to what I introduced here as the machine learning model. At a high level, what it means is that they assume additive bounded noise rather than sampling one element at a time or mini batches at a time, and these are completely different models. I will be happy to go over it in more detail if you are interested offline about this, okay, about the differences in the settings here. So, let me now jump to an outline of our results, and I will present it as the questions that we ask and what we get as an answer. So, the first question that we ask is whether it is possible to improve this linear dependence on the condition number to a square root condition number for all problems in the stochastic setting. And it turns out that the answer to this is no, and there are explicit cases where it is not possible information theoretically to do any better than the condition number. So, the second question would then be whether improvement is ever possible. Let us say for some easier problems maybe improvement is possible, and the answer to this is actually subtle, and it turns out that it is perhaps possible, but it has to depend on other problem parameters. It cannot just depend on the condition number. Okay. Then the third question that we ask is whether existing algorithms like stochastic heavy ball and stochastic Nesterov's accelerated gradient, which are actually being used in practice, do they achieve this improvement whenever it is possible on problems where it is possible. And the surprising answer to this is that they do not, and in fact there are problem instances where they are no better than SGD, even though improvement might be possible. Okay. And finally, the question we ask is whether we can design an algorithm which improves over stochastic gradient descent whenever it is possible, and we do design such an algorithm which we call accelerated stochastic gradient descent, or ASGD for short. So, let me try to go a bit more detail into each of these things. Are there any questions at this point? Okay. So, let us first try to answer the first question, whether acceleration is always possible in the stochastic setting, and we will try to do this with examples, and the example that we consider examples we consider will be the noiseless case where y is exactly equal to x transpose w star for some vector w star, and the question we are asking is whether we can improve the convergence rate of stochastic gradient descent from a linear dependence on condition number to maybe a square root on the condition number. Okay. For this, let us consider a discrete distribution. So, here we said y is equal to x transpose w star, and w star is some fixed vector. So, all I need to specify is the distribution of x, and here I am specifying the distribution on x. So, let us say x is equal to is a 2-dimensional vector, 1 0 with very high probability 0.9999 and 0 1 with very low probability 0.0001. In this case, an easy computation tells us that the condition number is 1 over the minimum probability, which is 10 to the 4. And the question we are asking is if we can get a convergence rate that looks like square root condition number, or equivalently if we can halve the initial error using about square root condition number samples, or about 100 samples, right. And in this case, it turns out that it is actually not possible, and this is not too difficult to see because if we sample a bunch of samples from this distribution, unless we see about condition number of samples, we will not see the second direction, which is with probability 10 to the minus 4, right. With fewer than 10 to the 4 samples, then we do not see anything in this 0 1 direction, any x in the 0 1 direction. So, there is no way we can estimate our the second coordinate of w star without looking at this the 0 1 vector. So, with fewer than condition number of samples, we cannot actually estimate anything about w 1 star. So, acceleration is not possible in this setting. So, this answers our first question in the negative, that there are some distributions where acceleration may not just be possible, information theoretical. Yeah.
So here, second coordinate of w1 star is 1 over kappa anyway.
Yeah. So it depends on
less than 1 over kappa.
Yeah.
You can always estimate it with one sample.
Yeah. Yeah. So it depends on what is your noise level. So if you are above some noise level, then you don't care about that coordinate. If you are below that noise level, when you do want to get that right,
yeah,
you care about it.
Hugely nonlinear dependence on epsilon on your desired accuracy.
Yeah, so it does depend on epsilon. And however, when I am talking about the rates here, this rate, like if I give you a certain rate, either you have to write it in terms of till this error I get this rate, till this error I get a different rate, or if you are trying to write a universal rate, you do want to understand what is the real behavior of the algorithm. Yeah, but that's all I am saying.
Dependency on epsilon is log 1 over, is minus log epsilon, which is not as nonlinear as the dependency here.
Can I get you?
You do have dependency on epsilon in your formula.
Yeah.
Minus log epsilon.
Yeah. So if you are allowed to if you are allowed to depend on epsilon as well, then the dependency will be like something good till you want to get to 1 over kappa accuracy, and something different after you, like if you want to go below 1 over kappa accuracy. Yeah.
Sorry,
Okay. Yeah.
Intuitively, the second dimension matters a lot less than the first dimension.
Yeah.
Right? Because it's so rare that you'll ever see that
Yeah.
direction.
Yeah.
But why isn't observing the first dimension enough to get very high or very low error?
Yeah, so that's what I was saying. So if you only care about error which does not care you, okay. So one thing you can think of is you could be so far away from your optimal in the second direction that even with the low probability, when you take an expectation, it could actually matter.
Yes, if the loss is super large.
If the loss is super large. But the point I am trying to make here is that if you only care about a certain level of accuracy, then you don't care about the second coordinate. If you really care about the entire spectrum of rate, then you do care about the second one as well, because eventually you want to get everything right. And this example seems kind of cooked up, but the point of this example is to illustrate the issues that might arise when you think of acceleration when you go from a deterministic setting to a stochastic setting. So when I go to maybe empirical evaluations, things may be much clearer. But at this point, this example is more to illustrate like what are the things that could just be completely different between deterministic and stochastic settings.
So for example, if the loss is bounded like in classification,
Yeah.
error, then this would not be an issue. Because you can.
So this may not be an issue. I mean, you could also think of, for instance, where one dimension is actually super large, but there are a lot of other dimensions which together matter a lot. But then you are still restricted in your step size because of the single large direction, where this might still be an issue, right? Okay. So this basically demonstrates that you cannot expect this acceleration phenomenon to always magically work out in the stochastic case. And the second question then we would ask is whether it's ever possible for this acceleration phenomenon to still help you in the stochastic setting, right? And for this we again take a two-dimensional example where the vectors come from a Gaussian distribution and the covariance matrix is diagonal with 0.9999 and 0.0001, the same values we had earlier. And even in this case, the condition number turns out to be about 10 to the 4, right? However, because this is a Gaussian distribution, if you just observe two samples with probability 1, they are going to be linearly independent, right? And once you have linearly independent samples, you can just invert them to exactly find W star. So no matter how large the condition number is, just after two samples, you are able to exactly find W star, right? And in this setting, this suggests that acceleration might be possible, at least from an information theoretic point of view or statistical point of view. So for the second question, we see that it might be possible, but it has to depend on something else and not just the condition number. Okay. So what is this quantity that actually distinguishes the previous two cases of the discrete and Gaussian distributions? And the answer is basically the number of samples that are required for the empirical covariance matrix, which is this 1 over n summation xi transpose minus the actual covariance matrix H. So as long as our empirical covariance matrix is close to the true covariance matrix, we are okay. And the important quantity here is what is the number of samples that you need for this to be the case. For scalars, this is very well understood, and it's just the variance of the random variables that you are considering. And for matrices, there is a similar notion called matrix variance, which in this context we denote by kappa twiddle and call it statistical condition number. This is the quantity which determines how quickly the empirical covariance matrix converges to the true covariance matrix, right? And this quantity is what really distinguishes the previous two cases. So how does this actually relate to the actual condition number? So if we recall, the computational condition number, or just the condition number, which is here on the right, is just the, let's say, the maximum norm of x square over the support. We can relax this, but for simplicity, let's say the maximum norm square over the support of the distribution divided by the smallest eigenvalue of the covariance matrix. So that's the definition of condition number. Whereas the statistical condition number is here on the left, for an appropriate orthonormal basis E, this is basically a weighted average of the mass on the direction E divided by the expected value of E transpose xi whole square. So the expressions may look a little complicated, but once you have these, it is actually not too difficult to see that the statistical condition number is always less than or equal to condition number, because on the left you have some weighted average, whereas on the right you have a minimum in the denominator. That is basically the intuition, and this can be formalized, and acceleration might be possible whenever the statistical condition number is much smaller than condition number. Okay? Because statistical condition number, we are thinking of it as an information theoretic lower bound. So, if kappa twiddle is pretty much the same as kappa, then there is no acceleration to be had, whereas if kappa twiddle is actually much smaller than kappa, there may be scope for accelerating the rate of stochastic gradient descent.
Sorry, what's the sum over E?
Yeah, so this was a little complicated, so I tried to simplify it. So E is basically the eigenvectors of the covariance matrix, of the covariance matrix H, population covariance matrix H, and
so their utmost D.
yeah, this is like D for Gaussian random variables, yeah, whereas that could be arbitrarily large. Yeah. Okay, so if we compare what happens for the discrete and Gaussian cases, so for the discrete case, it turns out that both the statistical and computational condition number are about 10 to the 4, which are essentially the same, and so that is why we see that acceleration is not possible in that setting. Whereas in the Gaussian setting, with some constants, so the statistical condition number is of the order of about 100, whereas the actual condition number is about 10 to the 4. So there is a significant difference between the statistical and computational condition numbers, and this was the reason why discrete case acceleration is not possible, and where in the Gaussian case there is still hope that acceleration might be possible. Okay, and if we plot this. Plot the performance of stochastic gradient descent for both of these distributions. So, the left is discrete and the right one is Gaussian. The green curve corresponds to the error of stochastic gradient descent over several iterations, and we see that the point where the error starts to decay is pretty much the same for both of them, and it is about the condition number. So, after the condition number of samples, it starts to really decay geometrically, whereas the statistical condition number in both these cases is very different. For the discrete distribution, there is not much difference between kappa twiddle and kappa, whereas for the Gaussian distribution, there is a lot of difference between the statistical condition number, which is the information theoretic lower bound, to the place where stochastic gradient descent actually starts doing very well, right. So, there is a large gap between the pink line and where green line starts to do very well for the Gaussian distribution. Okay. So, this next question would then be whether existing stochastic algorithms such as stochastic heavy ball or stochastic Nesterov accelerated gradient, do they achieve any improvement in settings like this Gaussian setting that we saw before, where there seems to be a scope for acceleration. And the surprising answer to this is that actually we construct explicit distributions and fairly natural distributions, not cooked up distributions, where there is a large gap between statistical and actual condition number, but the rate of heavy ball, the stochastic heavy ball method, is no better than that of stochastic gradient descent. So, in the stochastic setting, even though there is scope for improvement on certain problems, stochastic heavy ball does not achieve this improvement. We can show this rigorously only for the heavy ball method, but the same intuition seems to be true, same result seems to be true empirically even for stochastic Nesterov's accelerated gradient as well. So, what I mean by that is that if you look at, so this is the lower bound, I would hope that and green one is stochastic gradient descent. I would hope that an accelerated method can do much better than stochastic gradient descent, but it turns out that the stochastic heavy ball, which is in blue, and stochastic Nesterov, which is in black, they basically are on top of each other and they do not do much better than stochastic gradient descent. So, these momentum techniques do not really help in the stochastic setting here. Yeah?
So if you did this deterministically, you would expect to have a dip along this purple line, or
yeah. So, if you use any of the offline methods, right, then using these number of samples is sufficient to start decaying the error. Yeah.
Is it with noise or without?
This is without noise, but we have similar plots for with noise, but then there is an error floor which is of like 1 over n. Yeah. So this is without noise.
So the dip should happen at 2 samples.
Okay.
If you're talking about the direct method.
It depends on the dimension.
Yeah. So I haven't plotted the direct methods here. Direct methods. So there are these two things are decoupled, right? So there is how many samples do you take to construct your empirical loss function, and how many iterations of your direct method that you run. So there are like both of these are decoupled for direct methods.
Okay, but just checking the answer to the last question is, if you did a batch method, direct method, or whatever, on 2 samples, it would work. It would get
on 2 samples for the Gaussian distribution, it should just work. Yeah, exactly. But the number of iterations it would take might still be larger, because the empirical covariance matrix might still be very ill conditioned.
You mean if you use Jacobi to compute the eigenvalues, it might take.
Then if you completely, like if you use a matrix inversion, then it will be like just quick. If you again use a first order method to solve the empirical loss function, that could take some while, because the empirical function is not very well conditioned. Yeah, that's all I meant. Okay. So the point of this plot is that the stochastic momentum methods in the stochastic setting do not really provide the improvement that we expect them to provide based on our intuitions from the deterministic setting. Okay. So finally, so the question is whether we can actually design an algorithm which actually gives these kind of improvements in the stochastic setting whenever such improvements are possible, right? And the answer to this actually turns out to be yes, and we design an accelerated stochastic gradient descent method which gets the following convergence rate. So the second term, which is sigma square d over epsilon, is the part that comes due to noise, and the first part was what we were looking to improve for. Compared to stochastic gradient descent, which has linear dependence on kappa, our method has a dependence on square root of kappa twiddle, and we already saw that this kappa twiddle is always less than or equal to kappa. So this result is always better than the condition number, okay, and that could be much better when there is a large gap between kappa twiddle and kappa. So what does this mean in terms of plots? So note that this is the x-axis is in the log scale. So the green one is stochastic gradient descent, the blue and black which overlap are the stochastic momentum methods, and the red curve is our algorithm. And at least in this case, we see that there is about an order of magnitude improvement in the performance of our method compared to that of stochastic gradient descent or even the stochastic momentum methods. Okay. And I would so we should also note that we are still far away from the lower bound, which is about 100 here, and we believe that while information theoretically 100 samples might be sufficient for computational methods or streaming computational methods like which are based on this first order information, we believe that it may not be possible to do better than whatever our result is, but we do not have any proof of this statement. This is just a conjecture at this point. Okay.
Is this still the 2D Gaussian example?
This is actually a 100-dimensional Gaussian example.
Okay, so coming back to your question,
Yeah.
2 samples not enough, right?
Yeah, in this case, so that's why I put it at 100. Yeah,
Lower bound is
100.
right?
Yeah.
Okay.
And this is the same graph as before. So previously.
Yeah. So all the graphs are the same thing. Yeah. Yeah.
Just about these bounds. So in your methods, you showed that the convergence rate is actually a square root kappa tilde.
Yeah.
So that doesn't correspond to the lower bound that you've noted here.
Yeah, so that's what so there is still a gap between the kappa twiddle here, like both theoretically and empirically we do see that there is this gap. We don't know if it is possible to achieve the lower bound with a streaming algorithm like the one that we are using. Yeah. You can definitely achieve that by using a batch kind of method, but with a streaming method it's not clear.
Sorry, my brain is going slowly. What is the value of square root kappa tilde here? Is it 100?
Here
Or is it like 300 or something?
10 cube, about 1,000.
It's 1,000. Okay.
Yeah. Okay. So let me now introduce briefly the algorithm that we use, and unfortunately we ourselves don't have too much intuition about what exactly it is, but at high level what I want to point out is that in the deterministic setting you could write Nesterov's accelerated gradient in several different ways. The most popular one is a 2-iterate version which has this momentum interpretation, and there is also there are also various other interpretations of understanding what Nesterov's acceleration is doing. There is another interpretation which uses say 4 iterates and has this interpretation of simultaneously optimizing upper bounds and lower bounds for the function that you are trying to minimize. Okay. While all of these are equivalent in the deterministic setting, meaning that when you use exact gradients, they actually turn out to be quite different if you use stochastic gradients instead of deterministic gradients. And the algorithm that we analyze here is basically Nesterov's accelerated gradient in the 4 iterate version, and we again basically replace the gradients with stochastic gradients. In our paper, we explain this more as how this relates to a weighted average of all the path gradients and so on, and I will be happy to talk more about it offline if you are more interested in knowing what exactly the algorithm is doing. Okay. So, for the next couple of slides, let me try to give a high level proof overview of the result that we have here. Yeah.
I couldn't parse the algorithm so quickly, but computationally, is it comparable to the two?
Yeah, so up to constant it's the same. Like instead of 2, it will be 4 or so. Yeah. Okay. So if you recall our result, so this is our result, right? So there are 2 parts to the result. One is the rate because of the noiseless part, the other one is due to the noise term, and the proof also naturally decomposes into 2 parts. One for the one to bound the first term and the other one to bound the second term. And for the first term, we can just assume that we have a noiseless setting and just analyze what is the convergence rate in the noiseless setting. And for the second term, you assume that you start at the right point and just understand how this noise drives the algorithmic process. Okay. So these are the 2 different components of the proof, and the first part actually is fairly straightforward once we figure out the right potential function to use. And the main innovation that we had to do here was that for the standard Nesterov's accelerated gradient, there is one potential function that's actually used, and then we realized that there is actually a family of potential functions that you could use, which all of them work for the deterministic setting, but only one of them seems more suitable for the stochastic setting. And so if we shift the potential function by the H inverse norm, it turns out that this is the right potential function, and the analysis is actually fairly standard in that it follows the kind of analysis that deterministic Nesterov's accelerated gradient follows. Okay. Okay. So and then you get this geometric decay rate of 1 minus 1 over square root kappa kappa twiddle, and this is where the geometric decay of square root kappa kappa twiddle comes from. For the second term, it turns out that such a simple analysis actually does not work out, in the sense that if we try to use any potential function, it seems to blow up our results by a factor of dimension or factor of condition number. So we had to do an extremely tight analysis of how the stochastic process evolves when it's driven by the noise. So you can think of the algorithm as a process, something that describes the process, and noise as something which comes in as an input at every time step, and you have to understand how the algorithm behaves in this noise input, right? And basically, if you think of 2 iterates of the algorithm, which is say Wt and Ut, then we write theta t to be the covariance matrix of these iterates, and then we can write a linear system that describes the evolution of these covariance matrices theta t. Okay. And if you do all of this, you get this inverse formula where B is an operator which takes positive semi-definite matrices to positive semi-definite matrices. Okay. So, and you want to understand what happens to I minus B inverse applied to this noise transpose matrix, and this is still quite challenging because B has singular values which are larger than 1. So, if we use any crude bounds, we cannot even get a good bound on this one. So, we had to really understand the eigenvalues of this operator B, and then solve this inversion problem in 1 dimension, and then combine different dimensions together using bounds on statistical condition number and condition number. Okay. So this is all I wanted to say about the proof of the result. So if we recap whatever we have seen so far, we saw that for the special case of stochastic linear regression, we can completely theoretically understand the behavior of stochastic gradient descent, stochastic momentum methods, and this new accelerated stochastic gradient descent method. And we saw that while conventional methods do not really provide any improvement in this setting, this new method seems to provide significant improvement even in the stochastic setting. So, the next question that we were trying to tackle is whether this has any relation to problems beyond linear regression, or is it just a special or just this applies only to linear regression, right. And so, we had a bunch of conjectures or results here, and we tried to evaluate all of them in the context of training neural networks. So, the first question that one comes to mind when we go into this new setting is that people are actually using stochastic heavy ball, stochastic Nesterov in practice, and there are also been very influential papers which argue that they actually give improvements over stochastic gradient descent, and this is why people started using these methods in the first place. Whereas, what we are saying here is that these momentum methods do not really give any benefit in the stochastic setting. So, both of these things are contradicting to each other, and what is the reason for this apparent contradiction? And the reason here turns out to be mini batching. So, if you think of mini batching, it is actually a continuum between like completely stochastic setting and a completely deterministic setting based on the size of mini batch that you actually choose, right. And what we are saying here is that in the extreme where the mini batching is 1 or completely stochastic case, these momentum methods are not helping, whereas in the deterministic case we know for a fact that these momentum methods actually help. And when you are using mini batching somewhere in the middle, it is conceivable that you are going to get benefits purely because you are moving somewhat closer to deterministic gradient descent. Okay. And the point of our algorithm here, however, is that ASGD improves over SGD irrespective of what mini batch size it is, and for whatever mini batch size, if there is anything acceleration that is possible, it gives that kind of acceleration. So, in order to test this hypothesis, so we first trained a deep autoencoder for MNIST with the smallest batch size of 1. So, stochastic gradients on single examples, and it turns out that the performance of stochastic gradient, heavy ball and Nesterov are essentially similar. There is nothing really to distinguish the difference between these methods. Whereas, if we run our accelerated stochastic gradient method, it runs reasonably faster, at least in the initial part, compared to that of these other algorithms, right, even with a small mini batch size of 1. Even going next to classification task on CFAR10 using a ResNet with again a small mini batch size of 8, which is much smaller than what is used in practice. If we use this mini batch size of 8, we again see that there is not much to distinguish the performance of stochastic gradient as well as the stochastic momentum methods. So, all of them kind of perform reasonably similar. Whereas, if you compare our method with for instance Nesterov method here for example, at least in the beginning phases it converges much faster compared to the Nesterov method, and we only really think about the initial phases because there is this additional term of sigma square d over n which I did not talk about. So, eventually you will reach the noise floor and then there will be no acceleration in that part. So, the acceleration that you can hope for is only in the initial phases where you can hope to get faster convergence. Okay.
Are you using the same learning rate decay?
Yeah, so that is why the drops are kind of correlated, but the learning rates themselves have been surged using hyperparameter surge. Yeah.
And how about the other parameters?
So, we only use so in the previous thing it was just a constant learning rate, so there was no decay. Here the things that we search for are learning rate, when to decay and how much to decay. All of this was based on a validation set, and then we use this and these are test 0 and test error. Yeah.
You just answered my question.
Okay. Yeah.
How's the error when it's at convergence, after convergence?
So, so I guess yeah. So here you can see it's about 90. So 8%, about 8% is the error that you get here. It's not maybe fully state of the art, but then we are also not using like a state of the art network to do this.
And there's no real difference between both methods.
Yeah. So the final error, there is not that much of a difference. The final error seems kind of similar.
So what you're saying is if you only have time for 10 passes, you should use ASGD.
Yeah, yeah. So I mean that's actually my next thing. So okay, so this was for like small mini batch size of 8, right? So if you use something like 128, which is more reasonable to use in practice, we again see that ASGD converges faster, but pretty much to the same accuracy, but it converges faster compared to Nesterov method. And of course, I mean you're again seeing these similar places to drop, because that's exactly where we decay the learning rate. And if you, for instance, if you only care about getting say to 90% accuracy, you can get there using ASGD about 1.5 times faster as compared to Nesterov's method. And this could potentially be useful for if you are doing hyperparameter search and you don't care about getting the optimal error for every hyperparameter, but only want to figure out what is the rough ballpark that the error is going to be. Okay.
But that's a kind of, there's a jump there, right? You can't really predict how
Yeah.
the error is going to be after 100 epochs.
Yeah.
And
Yeah.
how fast
Yeah.
initially
Yeah.
conversions will be.
Yeah. Yeah. I mean, if you only want to see whether something is extremely bad or it's reasonable,
Right.
this could help you. That's all. That's all I'm saying. Yeah. So okay. So this brings me to the conclusion of my talk. So to recap what we have seen, in the deterministic case, we saw that acceleration improves the convergence speed of gradient descent by a factor of square root condition number, and we asked the same question in the stochastic approximation setting, where we saw that stochastic momentum methods, which are like the conventional and classical methods that are being used, they do not achieve any improvement over stochastic gradient descent, whereas the algorithm that we propose, which is accelerated stochastic gradient descent, can achieve acceleration in the stochastic setting whenever it's possible. And while our theoretical results have been established only for the stochastic linear regression problem, we also empirically verify these observations for in the context of training deep neural networks. And we have also released code for this algorithm in PyTorch. And if any of you play with neural networks, we would encourage you to try out our algorithm and let us know what you observe. So just as a high level point about optimization in neural networks and so on, I would like to point out that while optimization methods are heavily used in training neural networks, a lot of the methods that are actually used are not well understood even in like very benign setting such as convex optimization. I spoke about like momentum methods, stochastic momentum methods, even for the special case of linear regression was not really well understood. And algorithms such as ADAM, RMS prop, there has been some recent work on ADAM, for instance. So there are a bunch of these methods which are widely used in practice, but even in very benign settings, their performance is not really well understood. And it's important to do this because, as we saw, just because people are using it, it may not be the best thing to do. As practitioners, we may not have all the time in the world to try out all possible combinations to figure out what is the best thing to do, right? So and in this context, stochastic approximation from a theory point of view provides a good framework to understand these algorithms, to see what makes sense and what does not make sense. And while classical stochastic approximation results focus on asymptotic convergence rates and so on, we would be really interested here in obtaining strong non-asymptotic results, which give us like finite time convergence guarantees and so on. So that's all I had to say. Thank you for being here. Yeah.
On the Gaussian graphs, what was the y-axis again?
Error.
Yeah, what error?
Test error under the distribution.
So f of omega 0 minus
F star.
f star.
F of omega t minus f of
F
f star.
omega t minus f star.
Yeah.
Okay, on some other draws from the same distribution.
In this case, we can exactly compute the function value because you know that it's a Gaussian distribution. So you know the covariance matrix, right?
Right.
So it only depends on the covariance matrix. Yeah.
So your new algorithm, the accelerated stochastic gradient, if you do that for deterministic, does it have a correspondence to some other known algorithms, or how did you come up
Yeah, so as I said, right, so Nesterov's accelerated gradient can be written in multiple ways in the deterministic world. The most popular one is what has this momentum interpretation, and which is what people use. But there are various other interpretations and various other ways you could write the same algorithm in the deterministic world, and our algorithm is stochastifying one of them. Yeah. So in the stochastic world, they are completely different, even though in the deterministic world they are exactly the same.
So your bound square root of kappa kappa tilde was that an upper bound?
That's an upper bound, yeah.
But in the plot, it wasn't, the error wasn't going down around 10
So-
to the 3. So that's,
So there may be some other constant, but
so you would expect it to go down at 10 to the 3, or
Yeah, it is.
yeah, so it hasn't hit the bottom. So if you consider like 10 to the 4 as the baseline for these methods, so right after 10 to the 4, like they curve down.
is there a more kind of quantitative way to
Yeah, so
verify?
there was a more quantitative way, which is that ideally you want to run this for different values of condition number and see, and then like plot the line and see the slope of that line,
Yeah.
which also we have. It's a little more difficult to explain than
I
talk.
see.
Yeah.
Well, there are no more questions. Let's thank Praneet again.
Thank you.